Every time you open an app, your request doesn't go to one giant server. It goes to a load balancer, and the load balancer decides which of many identical servers should actually handle it. That one decision is the whole game. Make it right and the system feels instant, invisible to the user. Make it wrong, and a single server melts under the pressure while the rest sit idle. So today we'll walk through 6 ways to make that decision. 6 load balancing algorithms. The setup is the same every time. A client on the left, the load balancer in the middle, 3 servers on the right. All that changes is how the balancer picks, and which server the request lands on. The simplest way to spread the load is to just take turns. That's round robin. The load balancer keeps a fixed order and cycles through the servers one by one. It's simple, it's stateless. The balancer remembers nothing except whose turn is next. And it's completely predictable. The first request goes to server 1. The next request goes to server 2. The one after that goes to server 3. And then it wraps right back around to server 1 and starts the cycle again. The catch is right there in that predictability. Round robin has no idea how busy each server actually is. But your servers usually aren't identical. One might be a beefy machine, another an older, smaller box. Weighted round robin fixes that by giving every server a weight, basically a number that says how much it can handle. Here server 1 has a weight of 3, server 2 a weight of 2, and server 3 just 1. So for every 6 requests, 3 of them go to server 1, the strongest, 2 go to server 2, the middle one, and only 1 goes to server 3, the weakest. It's still a simple rotation, but now it's biased in proportion to each server's real capacity. This is the go-to when your hardware is a mix of old and new. Round robin is blind to what's happening right now. Least Connections opens its eyes. Instead of a fixed order, it looks at how many requests each server is currently handling. Server 1 has 5 open connections, server 3 has 8. But server 2 only has 2, so the balancer compares all 3 live connection counts. It rules out the 2 busy ones, server 1 and server 3, and commits the new request to server 2, the least busy. This is your go-to for long-lived, heavy connections. Think video streaming, WebSockets, or massive database queries, where one user can tie up a server for minutes at a time. The trade-off is that the balancer now has to keep live state. Sometimes you actually want the same user to keep hitting the same server, so their session stays put without copying it everywhere. That's IP hash. The balancer takes the client's IP address, runs it through a hash function, and takes that result modulo the number of servers. The math always lands on the same index for the same address. Here, this client's IP resolves to server 2. Now watch the important part. A second request from the exact same IP hits the hash, and lands on server 2 again. Same client, same server every single time. That's determinism. You get sticky sessions for free with no shared session store. The downside? If you add or remove a server, the math changes and stickiness breaks. To fix that, modern architectures upgrade this to consistent hashing, which keeps most sessions intact even when the cluster resizes. Least Connections asks who has the fewest requests, but a server can be handling only a few requests and still be slow. Least Response Time asks the sharper question, who is actually answering the fastest right now? Server 1 is taking 45 milliseconds, server 3 30, but server 2 is answering in just 12. The balancer continuously measures each server's response time. It sets aside the 2 slow ones and spots the fastest and routes the request to server 2 at 12 milliseconds. Because it's optimizing the thing your users literally feel, how long they wait. This usually gives the best perceived performance. All 5 algorithms so far assume every server is up and working, but servers crash, freeze, and get overloaded. And routing a request to a dead server means a failed request for a real user. Adaptive load balancing constantly runs health checks. Here servers 1 and 3 are healthy, but server 2 has failed its check. it's down. So watch what happens. The balancer detects that server 2 is unhealthy, and the health check flashes red. It refuses to send the request there at all. It steers away from the unhealthy node, and instead it routes around the failure to a healthy server, server 3. This is the most resilient of the 6 because it doesn't just balance load, it actively steers traffic away from trouble. So there are your 6. Round robin takes turns, weighted accounts for hardware. Least connections counts the active users. IP hash glues a user to a server. Least response time clocks the speed. And adaptive avoids the casualties. Here's the one idea to keep. The shape is always the same: client, balancer, servers, and every algorithm is just answering one question differently. Which metric do we trust to pick the server? Get that metric right for your workload, and the load balancer quietly keeps everything fast and online. So before you go, one question, and I genuinely want your answer. Imagine you're load balancing a live streaming app. The connections are long and uneven, some users stay for hours, and every now and then a server just falls over. Out of the 6 we covered, which algorithm would you reach for and why? Round robin, least connections, adaptive. There's a good case for a few of them, so make yours in the comments. And if this made load balancing finally click for you, do the one thing that really helps the channel. Drop a like, subscribe, and ring the bell so you catch the next one. I'll see you there.